In June of this year, the United States government told ASML it believed one of its machines had already reached China. Not a part. Not a component. An entire working EUV lithography system. ASML denied it immediately. And industry experts didn't just disagree, they laughed at the idea, because the machine in question weighs 180 tons, ships inside the belly of a cargo plane, and needs a specialized installation team weeks to even assemble on site. You cannot smuggle that in a suitcase, and you definitely cannot quietly wheel it through customs. Think about how strange that accusation actually was, for a second. This is a company most people have never even seen a photo of one of its own machines being accused of a leak so serious the U.S. Secretary of Commerce personally raised it. And the response from people who actually work in this industry wasn't fear. It was closer to disbelief. Because everyone who understands how these machines physically exist in the real world knew instantly how implausible smuggling one whole would actually be. So, if moving one of these machines is physically impossible, building your own from scratch should be even harder. That's exactly what China's been trying to do. And the specific piece everyone said couldn't be replicated isn't the laser, and it isn't even a single mirror. It's the entire optics system. Those mirrors have to work inside, together, in perfect sync, at a tolerance so extreme that engineers compare it to landing a laser beam on a golf ball sitting on the moon. Here's what China actually built, what's genuinely impossible about it, and what isn't, using verified reporting, not the panic or the dismissal you've probably already seen. There's a detail about halfway through this video that reframes the entire impossible claim, so stay with me on this one. Let's get into it. Here's the fast version first, because the scale of what's actually being attempted here needs to be understood before anything else makes sense. EUV lithography isn't one mirror doing one job. Inside the real machine, light gets bounced across a whole chain of mirrors, some shaping and directing the beam before it ever hits the wafer, others focusing it down to a pattern thousands of times thinner than a human hair. Depending on the exact system, that chain typically runs anywhere from 6 to 11 separate mirrors, each one individually more precisely shaped than almost any manufactured object on Earth, and every single one of them has to sit in exact alignment relative to every other mirror in the chain, inside a sealed vacuum, with essentially zero vibration, because a misalignment measured in a fraction of a nanometer at any single point in that chain ruins the entire exposure. This isn't a single hard part. It's an entire orchestra of hard parts that all have to stay perfectly in tune with each other, continuously, for years of factory use, without a single one ever drifting out of position. Only one company on Earth has ever built that complete optical chain at a level chipmakers can actually rely on. A German firm called Carl Zeiss, working inside a partnership with ASML that's now stretched across 2.5 decades and more than €1.5 billion of direct investment. Zeiss's revenue from that specific optics business has grown from roughly €1.2 billion to over $4 billion in less than a decade, entirely on the back of a technology so specialized that finishing a single one of the largest mirrors through a process called ion beam figuring that removes material one atom at a time can take close to a year of continuous work. That's the actual bar China's optics program is being measured against. Not one clever mirror. An entire precision chain nobody else has ever fully matched, built by a company whose entire optics division exists essentially for this one purpose. Now here's where the story most people have heard already comes back in, but with a piece almost nobody connected properly. Reuters reported that a classified Chinese program based in Shenzhen completed a working EUV prototype in early 2025, built in significant part by former ASML engineers operating under assumed identities specifically to keep the project hidden. According to detailed accounts of the build, the team didn't just attempt the light source. They built their own version of the optical mirror chain too, using domestically manufactured mirrors that fall short of Zeiss's precision. And they layered artificial intelligence-powered correction software directly on top of the hardware, specifically to compensate in real time for the exact alignment errors their own mirrors couldn't physically avoid. Think about what that engineering choice actually reveals about their entire strategy. Every other attempt at closing this gap that's been publicly discussed has focused on eventually matching Zeiss's manufacturing precision directly, through better materials, better polishing techniques, better quality control. This team apparently made a completely different bet. Instead of trying to out-manufacture Zeiss atom by atom, they built mirrors that are good enough to function, then used real-time computation to paper over the difference on every single exposure. It's the engineering equivalent of admitting you can't outrun someone, so you build a faster car instead. Sit with that for a second, because this is the detail that actually matters more than the machine itself. They didn't solve the precision problem. They built a system that guesses around it, continuously, on every single exposure. If a story like this, one where the real engineering trade-off matters more than the headline, is exactly what you come to this channel for, that's precisely why subscribing now means you catch the next update the moment it lands, not after every other channel has already flattened the nuance out of it. Here's the number that actually tells you whether that AI workaround is holding up. One detailed account of internal testing describes the prototype hitting roughly a 60% yield rate on test exposures. Real commercial chip production needs yields above 90% to actually be profitable at scale. So even by the most favorable version of this specific claim, the software patch is covering for a hardware gap that's still enormous, not closing it. And that gap doesn't shrink evenly either. Getting from 0 to 60% proves the basic concept works. Getting from 60 to 90% is historically where these kinds of engineering problems get exponentially harder, not easier, because you're no longer fixing obvious flaws. You're chasing increasingly rare, increasingly subtle failure points that only show up after thousands of repeated exposures. But here's why dismissing this as a rough copy misses something genuinely important too. Independent analysts who reviewed the leaked details, including researchers at Tom's Hardware and TechSpot, note the team reportedly sourced components from more than one dismantled source machine, including second-hand parts tied to Nikon and Canon, alongside older ASML equipment. Essentially, reverse engineering a working optics chain out of pieces scavenged from multiple unrelated manufacturers who never designed their components to work together in the first place. Building something that functions at all out of a mismatched parts bin and getting it to 60% yield instead of 0 is nothing. It's a genuinely difficult systems integration achievement, even if it's still a long way from the 90% commercial bar. Most engineers would tell you that getting components from 3 different manufacturers, none of whom coordinated with each other, to work together at nanometer-level precision is its own separate miracle, completely independent of whether the mirrors themselves match Zeiss's quality. Now here's the part that changes how you should actually weigh all of this, the detail I mentioned you'd want to stick around for. While China has been racing to catch up to ASML's current generation EUV machines, ASML hasn't been standing still waiting to be caught. It's already shipping a newer generation called High-NA EUV, machines with an even larger, even more complex optics chain, designed specifically for the chip nodes coming after this current generation. That means even in the best-case scenario, where China's optics program eventually closes the gap on today's ASML machines, it will have spent years catching up to a target that already moved. Analysts who track this exact industry describe it plainly. China isn't just behind. It's chasing a target that keeps accelerating away from where it started, and every year spent perfecting yesterday's technology is a year the leader spends building tomorrow's. Here's what makes that particular problem so hard to escape, too. High-NA machines don't just need a bigger, better version of the same optics chain. The physics scale differently at that level, meaning even if China perfectly cloned today's mirror system tomorrow, a meaningful chunk of that engineering knowledge wouldn't transfer directly to the next generation anyway. It's less like running a race against a competitor who's simply ahead, and more like chasing someone who keeps switching to a faster vehicle every time you get close. So here's the honest scorecard, because both the impossible panic and the it's just a bad copy dismissal are wrong in specific checkable ways. What's true? The optics chain genuinely is one of the hardest engineering problems in existence, and Zeiss's own sensors are precise enough that a reflected beam could theoretically be aimed at a target the size of a golf ball, sitting on the surface of the moon. Full replication of that exact precision, using conventional manufacturing alone, does look close to physically impossible on any near-term timeline. What's also true? China didn't try to match that precision directly. It built a lower precision physical system and layered software correction on top, which is a completely different engineering strategy, one nobody fully expected, and one that produced a working, if flawed, result faster than most Western analysts predicted. A fully functioning scanner, even a perfect one, still can't produce a single leading-edge chip completely on its own either, since real production also depends on specialized photoresists, protective pellicles, and photomasks that come from an entirely separate supply chain. Most coverage of this story ignores completely. That last point deserves a moment on its own, because it's genuinely easy to miss. Even if China's optics program eventually hits 90% yield on a machine as advanced as anything ASML sells, that machine still needs chemically precise photoresist coatings, ultra-thin protective pellicle membranes that shield the mask during exposure, and photomasks manufactured to their own extreme tolerances, none of which come from the same supply chain as the scanner itself. ASML's real advantage was never just one machine. It was 3 decades of coordinating an entire web of specialist suppliers who all had to solve their own separate, impossible problems at the same time, and stay coordinated while doing it. Watch the yield number over the next year, because closing the gap from 60% toward 90% is the actual number that decides whether the AI correction strategy is a genuine breakthrough or a permanent ceiling. Watch whether China's program targets today's standard EUV machines or leapfrogs straight toward matching high-NA instead, because chasing the older target is arguably pointless if the rest of the industry has already moved past it by the time any of this reaches real production. And watch the broader chain reaction too, because if a sealed 180-ton machine can spark this much suspicion just from an unverified accusation in June, imagine the response the day independent inspectors actually get hands-on China's own version and start comparing the two side by side. There's also a quieter signal worth watching, one that has nothing to do with yield numbers at all. Watch whether more former ASML or Zeiss employees turn up connected to this program over the coming year, because a single recruited engineer is a data point. But a pattern of departures specifically toward this exact effort would say something much louder about how seriously China is willing to invest in closing this gap through people rather than pure domestic invention. So where does that leave the actual claim in the title of this video? Was this physically impossible? In the narrow sense, Zeiss and ASML meant it, matching their exact manufacturing precision through conventional means. The evidence so far says yes, that specific bar genuinely hasn't been cleared. In the broader sense of building something that generates light, bounces it through a mirror chain, and produces a usable, if imperfect, exposure, the evidence says China already did the thing everyone said couldn't be done, just not the way anyone expected, and not yet at a level that threatens ASML's actual business. Both of those things are true at the same time. And that's exactly why a headline that just picks one side ends up misleading you either way. It's also worth remembering how that June accusation about a smuggled machine actually connects back to everything you just heard. If a genuine, fully functioning ASML system really is that hard to move, hide, and secretly operate, and industry experts treated the very idea with open skepticism, then building a rougher, lower precision version domestically, piece by piece inside a facility you fully control, was always going to be the more realistic path forward for China than trying to acquire the real thing intact. The smuggling accusation and the reverse engineering program aren't two separate stories. They're two different answers to the same underlying problem, and only one of them turned out to be something China could actually pull off. Drop one word right now before you go anywhere. Possible. If you think the AI correction strategy proves the impossible claim was always going to bend eventually. Impossible. If you think a 60% yield with software patched on top of it isn't really beating the problem at all. Type it now, then go watch exactly how the laser side of this same program is doing, because that piece is moving even faster than the optics are, and it changes this entire timeline again. That video breaks down the two separate Chinese teams working on the light source itself, using two completely different physics approaches, and one of those results already beat a European research benchmark that stood for years. If the optics side is this close to breaking through the impossible label, the laser side might already be past it.